In semiconductors, over half the steps where chips are being made, plasmas are used sort of throughout the whole process.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. In a computerized world, microchips and semiconductors are vitally important to how things all around you work, from phones and televisions to cars and streetlights. The fourth state of matter, plasmas, are involved in several aspects of how modern microelectronic components are manufactured, and understanding the physics of how plasmas work and how they can be precisely controlled becomes more important as devices and their parts get smaller. We're joined by Jeremiah Williams, a professor of physics at Wittenberg University, where his group focuses on basic research in experimental plasma physics, with applications to space environments and industrial plasmas. Dr. Williams is also a program director here at the U.S. National Science Foundation. Dr. Williams, thank you so much for joining me today.
Thank you for having me.
So I want to start with the big question. What is a plasma?
Plasmas are one of the four naturally occurring states of matter. And I like to think of it in terms of the other states of matter and how you can distinguish between them. And it really has to do with how things behave at the atomic level, at the level of the atoms and the molecules that make up the material. So if you think about a solid like this table here, what makes a solid unique is that the atoms and molecules interact very strongly with each other. And as a result, they're locked in place and they can't really move, right? That's what makes them rigid and a solid. Now, if you were to add energy to that, say take like an ice cube, right? Put it on the stove, turn the heat on, that energy is being transferred in and it's being added to the atoms and molecules, and it's causing these to start jiggle some. And as they jiggle more, which we quantify by the temperature, that interaction that's holding them together just because of how they interact with each other, that is not enough to keep them fixed rigidly in place. And as a result, we experience what's called a phase transition, and the ice melts and turns into a water. So now the atoms and molecules still interact strongly, but not so much that they're fixed in place and they can move around some. Now, if you add even more energy, what happens is that thermal energy, the jiggling, they cause the molecules to basically spread out and undergo another phase transition and turn into a gas. Right? And now at this point, the only time these atoms and molecules interact with each other is when they bump into each other. Right? So, if you want to understand what's happening with a gas, say like right here, some air molecules, you just really have to think about what's happening when they collide with each other at that location. Right? So these collisions determine everything. Now, if you add even more energy, atoms are made up of smaller things. Right? You've got protons and neutrons inside the nucleus, and you have electrons also. And these electrons interact with the nucleus and are sort of bound to that. But if you add enough energy, you can pull off the electrons. And now you end up with this mixture of positively charged ions. These are the atoms that have had an electron pulled off. The electrons, which are negatively charged. And then some neutral particles, depending on the kind of plasma you have. Now, because you've got this mixture of charged particles, they interact through collisions, but they also interact through long range, what we call electromagnetic forces, right? So if you have like a magnet on your fridge, magnets can interact at a distance. It's what we call a long range force. And so the behavior locally is determined not just by what's happening locally, but through these long range forces as well. And that's what a plasma is. So it's essentially an ionized gas.
Where do plasmas come from?
It depends on sort of the setting you're looking at. In terms of sort of where plasmas initially came from, Big Bang happened 13.8 billion years ago. And at that point, everything was in a plasma state because there was so much energy, right? And it literally took hundreds of thousands of years for that plasma to cool down and return to a gaseous state, right? So plasmas in some sense are the first of the four naturally occurring states of matter. Now, as things have cooled, plasmas are still around, but they're not as everything's no longer in the plasma state. And if we look in sort of the visible universe, what we can see, plasmas account for about 99% of what we see in the universe. In space, stars are basically plasmas, and you can think of them as basically plasma generators. They spit plasmas out into space. That's the solar wind, right, which comes and hits the Earth, creates the beautiful aurora that we sometimes see. On Earth, we happen to be in an environment where plasmas just aren't naturally existing, which is good because it's not necessarily a hospitable place. We would not do well if we were in that environment. But you can make plasmas. And so, depending on what you want to do with it, you have different ways of doing it, right? So if you want to make semiconductors. We use power supplies to do that. There's other applications like plasma welding, where you use a plasma to connect material, or plasma cutters where you use the plasma to cut. There's also applications in medicine where you can use plasmas to treat wounds. Agriculture where you can increase crop yields. So there's lots of practical applications. They're created by basically putting energy into the system to ionize the gas.
How do they use plasmas in industry?
It depends a little bit on the industry that you're looking at. Plasmas have lots of applications across industry. So if you think about medicine, plasmas are used in medicine for sterilization. So you can use it to clean the surgical tools before you use them. You can use it for wound treatment, where the plasmas create these radicals when you ionize the gas, and they basically interact with the wound and can speed up the healing process. You can see it in agriculture, where you would treat seeds or plants directly with a plasma, and it's been shown that you can increase the crop yield. It's used in water purification. The plasma basically treats the water to make it safe to drink. So that's one sort of avenue. You can expose materials to plasma to make it hydrophobic. So if you want your genes to repel water, you can treat your genes with plasma to do that. Right? Hydrophobic just means water doesn't want to stick to it. In semiconductors, used a lot. Over half the steps where chips are being made, plasmas are used sort of throughout the whole process, right? So when you want to make a semiconductor, any type of electronic device that you might make, you would start off with a silicon wafer. Right? These are basically 30 centimeter discs, right? So it's about a foot across, a little bit less. And the first thing you do is you treat that with a plasma to clean it. And then what you would do is you would create a mask, which is basically sort of the shape of the circuit that you want to make. And those are typically made by taking a laser, hitting a tin to create plasma. So like a little molten drop of tin that creates light, which will then basically create the pattern on the material. You can then use the plasma to basically etch away the material, or to add layers of material, or implant things so that you make it behave in the way that you want your chip to behave. And then you end up with your microchip at the end. So there's lots of practical applications and how they get used in industry.
How might you control a plasma in this case? So like if we're thinking about plasma etching.
It's a complicated process. The nice thing about plasmas is that because they're made up of these charged particles, you can use what we know from sort of basic physics and how charged particles behave in different types of fields, right? So if we think about us on Earth, if I were to let go of something, we all know that it's going to fall, right? And the reason that it falls is gravity, right? We can model that as a field, and basically the object wants to go from here to here, and gravity is what's pulling it down. Same thing sort of happens when we're dealing with ions and electrons that show up in a plasma, but in this case, they're charged. So we use electric and magnetic forces to control how they move, just like we would use gravity to control how something moves as it's falling. So you can create the plasma, and then you can basically tune the plasma, change the parameters of the plasma so you get it sort of just right, and then you can apply these fields to control how they move. But it's a complicated process, particularly as things get faster, right? As you said at the beginning, things get faster because things get smaller, right? And the features that we are dealing with when we're making these semiconductors, we're on the nanometer scale. Now, of course, that probably doesn't mean a whole lot because most people don't think about nanometers, right? But a couple of ways to think about that, if you were to pull out one of your hairs, you would say that that's 100 microns, roughly. It's about 100,000 times bigger than a nanometer. Another way that I like to think about it is if you were to take one of those silicon wafers that they use, right, about an inch across, and you were to blow that up to the size of the Earth, the size feature that we're dealing with in current generation semiconductors would be about 5 centimeters, so just around 2 inches. So we're dealing with really fine, small structures, which means that you have to have really fine control. And that, can you control plasmas? Yes. In principle, it's a relatively straightforward process, but the level of control that you have to have with these highly energetic particles so that they do damage in the way that you want, right? To remove the material or to add material on, it's very complicated.
What are some of the challenges at that scale with patterning, let's say?
For example, one case, if we think about memory, right, that shows up in your phones and your computers, these are three-dimensional structures, right? So we've gone from where everything's two-dimensional to now they're two-dimensional and really small and becoming three-dimensional. And so you can sort of think of it as when you're making one of these memory chips, you're basically stacking layers up. So you're building your skyscraper. And then you form these holes. And the way that you do that is you basically accelerate the ions that are in the plasma so that they hit the material and etch it away. Right? And when they come in, they're coming in at 300-ish times the speed of sound. So very, very fast. And you basically use that to then bore these holes, right? Now, these are the holes that they're boring out are much taller than they are wide, right? So they're like, 100 times deeper than they are wide. And so that would be like, you've built your skyscraper. Now you're going to put in the elevator shafts, right? And so you need to have these ions that come straight down and sort of bore your hole out. And if you're off by just a little bit, right, like say 1/10 of a degree, your elevator's 20% shaft is 20% wider at the base than it was at the top, and your elevator is not going to work, right? And so you really have to craft these, how you have to control the direction that these particles are moving very, very carefully, and at the energies that they're moving, so that they can remove the material in the controlled way that you want to.
How are NSF and industrial partners impacting this process?
There are a couple of ways that happen. At the NSF, the mission of our agency, it's not really a mission-driven agency, but when it was created by Congress 75 years ago, it was with the purpose of advancing science, right? And so what I really like about the NSF is that we fund what I'd like to think of as curiosity-driven research that we don't know where it's going to end up, but we're doing because it's an interesting science problem that the community has identified. And with that, you never know sort of where it's going to end up, but you often end up with sort of new understandings which can then be turned into something that industry might be interested in. One really nice example, there was a story on the NSF webpage within the last couple of months. We had a PI at UCLA, Walter Geckelman and Patrick Preble, and they worked with Lam Research. And Lam Research is, I think it's like an $18 billion a year company. They make the components that they sell to semiconductor manufacturers to make the chips. And this process started back in the years, are probably getting them wrong, but around 2005-ish, when Patrick had this idea of how to better control the direction of the ions, which would be very beneficial because you want to really control how the ions are moving to etch out and remove the material. And so he built something in his kitchen, which is great.
Is this a laser?
It was a plasma device. It was a device to make a plasma, and he had this idea that if you could control how you were making the plasma, so basically you sort of turn it on and off very quickly, and if you did it in just the right way, you could really sort of shape how the ions were moving in a way that would allow you to then do what they might want to do in making a semiconductor. And so, they worked on it for a bit. They brought it to industry. Industry was hesitant because it wasn't fully developed. And so they came to the National Science Foundation with a proposal, and it went through the peer review process that we do with all proposals. And it was, able to be funded. And it was funded through what's called the Goalie program, where basically it's being funded by core programs to do basic science, but with an industrial partner, in this case, Lam Research. And they went through a couple of cycles of that. And after about 10 years of funding, they had really lots of careful experimentation, figured out how to control the ions. And it was just released as a product. It's marketed as their direct drive technology. And it's now a product that you can go and buy. And it's sitting on floors in semiconductor manufacturing companies making electronics.
So that's a great example of coming from the fundamental research idea that I made this thing in my kitchen that could control this, and now it's being used in your devices.
I've got this neat idea. There's a lot of complicated physics, a lot of careful work, understanding how it works, and then working with the companies to translate that basic research into a commercial product.
I also want to spend some time talking about some of your background research stuff. And I want to ask you about dusty plasmas.
Yes.
Is this the kind of dust we see around us? Is it like skin? What are we talking about?
So the subfield of physics that I work in is, as you said, dusty plasmas. And basically, the definition of a plasma that I gave you earlier is a little bit misleading. That's sort of like the pure plasma that really doesn't exist in real life. Most plasmas have particulate matter in it, right? So if you think about space, it's filled with the plasma. And there's lots of stuff in space, right? Asteroids, meteors, comets, right? As the comet goes by the sun, you see the beautiful comet trail. Well, what's happening is the ice is being blasted off the comet, so you're getting little ice chunks. So there's lots of particles. Now, if these particles are sitting in a plasma, they're going to collect charges and become charged too, right? Because they're sitting in a plasma environment, which is a bunch of charged particles. Well, once they become charged, they become part of the plasma system. And to really understand everything that's going on, you need to treat the dust as a part of the plasma. So a dusty plasma is a plasma that has three charged species. You have the positive ions, the negatively charged electrons, and then the dust particles. And when we talk about dust is really any particulate matter, right? So there have been dusty plasma experiments where they have used pollen. If you think about the ionosphere, for people who do ham radio, right? In the summer, you can often communicate greater distances away. Well, the reason why is in the summer, the ionosphere is colder because of how the planet is oriented relative to the sun. And that leads to the formation of ice crystals. Well, the ice is particulate matter sitting in the ionosphere, which is a plasma. It becomes charged, and that changes how radio waves, right, can travel. So they aren't able to travel in the same way, and they reflect off, and so you're able to see, communicate further away. All right, so it can be ice, it can be any matter. It could be skin. I wouldn't want to put skin in one of my devices. What we typically use are small particles that are grown in the laboratory, so we have a sense of what they are. Right, so they're typically some sort of plastic or silica or glass. We tend to use dust that is much more precisely manufactured, so we know exactly what it is. Right, and that allows us to better understand what's going on.
Very cool. Yeah. So for my last question, I want to ask about the future and emerging technologies. Where would you like to see the field go, or where do you think it will go?
If we're talking about plasma physics generally, that's a complicated question because plasmas are very broad, right? So if we think about the plasma physics portfolio that we have here at the NSF, we support low temperature plasmas, the types of things that I do. And on that side, there's lots of open questions. What is the charge on the dust? That's not fully understood, but it's an important quantity. We now have the ability to make very large magnetic fields, and that's a new knob that we can use to look at additional behavior. There's a project at Auburn University, the magnetized dusty plasma experiment. It was built with an MRI award from the National Science Foundation just over 10 years ago. That's a new knob that allows us to look at things, right? So as we think about going to the moon and Mars, well, you've got dust contamination is a real issue. So being able to control the dust is important. So I think there are lots of sort of interesting questions there. But that's just a small piece. You have high intensity lasers where you use lasers to do lots of really interesting plasma physics. There's the Zeus facility at University of Michigan that is now operational. They just hit the 2 petawatt, so the highest power laser in the U.S. And you can use that to accelerate particles, so that would enable the next generation of particle physics experiments. But there's a lot of medical applications for that as well. You can create extreme environments where it's relevant to what's happening inside of stars and inside of planets. Right, so the huge parameter space to look at there. There's currently a design project to try and push the frontiers further. That's the NSF Opal project, which is at the University of Rochester. The end result, that's a 3-year award that at the end they'll have basically a plan to build the next generation, right? And if that were to be funded, instead of having Zeus will be 3 petawatts fairly soon, this would be a 2 25 petawatt beams, right? And that would allow us to do things like boil the vacuum to create particles out of nothing, right? Which is just cool stuff.
It starts to get to where it's like, what is that?
All right. So, there's that, if you think about fusion, that's another example of plasmas. And there's a lot of questions there. How does the plasma interact with the wall, right? And, NSF funds this type of, is NSF going to fund we're going to build a fusion reactor? No, but are we going to address questions that are relevant to fusion? Absolutely, right?
Might do the science that gets us there.
Exactly. Exactly. Plasma physics isn't just in the division of physics, which is where I sit. You've got geospace, right? And in there, they look at the sun and Earth and that connection, as well as what happens inside the atmosphere. A lot of plasma physics there. Space weather, right? We've got lots of satellites. Being able to understand that and predict that's a big area where I think there's lots of opportunity. In engineering, there's a lot of plasma physics that's supported there. In manufacturing, and just trying to understand the engineering processes. So there's additional plasma physics there. If you think about semiconductor manufacturing, I think that there's a lot of exciting possibilities. That's going to be driven by market needs and then regulations, and those are hard to predict, right? But I think the one thing that is safe to say is that we are going to want things that are faster and more energy efficient. And there's a lot of questions that come in there, right? I could see lots of interesting examples of artificial intelligence, right? When a lot of these semiconductors are made, they come up with what you might call recipes, right? I want this power at this frequency for this long with these different conditions, because that's going to get the plasma close to sort of making what you want. The reality is, when you're doing that, there are lots of knobs that you have to turn, and those knobs have lots of settings, which make it impossible to find the optimal one. But you can run several case scenarios, and then maybe you could use machine learning to say, here's our input set, here's what the output is, here's what we really want, what's the optimal setting, right? So you could really sort of fine tune that. You can do these digital twins where you make a digital replica of the semiconductor device. And, we've just awarded something where they're helping to develop these models that will allow sort of full-scale modeling of the system to really understand what's happening, to sort of help drive that process of fine-tuning things to really get the right type of environment to make the kinds of things that you want. So I think there's lots of exciting opportunities. Just depends on sort of what you mean by plasmas, because plasmas really are broad.
Special thanks to Jeremiah Williams. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.